So I'm going to talk a little bit about Mars, ancient Mars, and why we're going there, and what's up with the Curiosity rover, which is still going and has been there for more than 9 years. But to the left, you see there are many missions to Mars, and this one's currently operating. It's called Methane, and it's basically trying to understand how the atmosphere of Mars was lost and what's going on in the upper atmosphere of Mars. So it's orbiting, and the Curiosity rover is on the surface. But let me give you a little bit of background. You know, what's driving us to do all these missions is a lot of work to get something to Mars or get something to space. And so the big questions that I think you'll all appreciate is, are we alone in the universe? Is there life in the universe other than on Earth? And so one way of looking beyond our solar system is the James Webb Space Telescope. It's a follow-on to the Hubble telescope, and it just got launched a few days ago, and it's on its way to start taking measurements. You'll hear about that this summer. It's going to see further into space than we've ever seen before. But even way back in 1610, Galileo, one of the first telescopes, looked out and found Jupiter and found that there were satellites, moons orbiting Jupiter. And so that really transformed our understanding. In other words, previously, a lot of folks thought that Earth was the center of everything. And here there's evidence that, Earth is not necessarily the center of everything. And so that was kind of really fundamental. And so 410 years later, that was 2 years ago, this big telescope was being assembled at Goddard in the building right up from where I work. So it's really exciting to see it. It's on its way to space. And places that we've sent spacecraft to are listed in this diagram: missions to asteroids, missions to Jupiter. There's a mission being developed to go to Venus, but Mars and the Moon have gotten lots of attention. And so you can see in the bottom left in the inset, all the orbiters that have been at Mars. Several of them are still going. And then on the surface, Curiosity was followed by the Perseverance rover. And I'll talk a little bit about the Rosalind Franklin rover that's going to be launched this year. So if we're really trying to understand whether life exists anywhere other than in Earth, where do we look? Well, on Mars is a good place to look, because even now there's some water probably in certain locations on Mars, and there certainly was water in the past, but there is water on moons of Jupiter and Saturn, and they're under oceans, under ices. And so those missions are in progress. And so in future years, we should learn a lot about whether life, for example, microbial life, very simple life, could have developed on these worlds. Venus is interesting because it's closer to the sun. It has a really big, thick atmosphere. It's really hot, 467 degrees centigrade, which is pushing 900 degrees Fahrenheit. And the pressure at the surface is very hot. So you wouldn't imagine that there could be any microbes living there. They would all fry. But up in the clouds, it's much more benign. Temperatures and pressures closer to what we have on Earth. And so it was really interesting when a team detected phosphine gas in the clouds of Venus and thought that, well, maybe that's coming from microbial activity. So what are the tools that we bring to the exploration looking for life? I'll talk a little bit about the ExoMars rover, the Rosalind Franklin rover, which is going to launch this year. Be a pretty exciting time. And then we're developing a mission to go to a moon of Saturn called Titan, which is just full of carbon. It has lots of methane in the atmosphere. And it's a really interesting mission. It's going to parachute in, but then a drone, a rotorcraft, is going to deploy and basically land, but then fly around the planet for many, many weeks and try and understand the chemistry and maybe even are there prebiotic type organic compounds there. But what we're going to talk about today is the Curiosity rover. And here it is in an artist's conception, but all the labels kind of show all the tremendous amount of instrumentation and tools that we have at our disposal. For example, in the upper center with the red light zapping out of it is what's called ChemCam. It basically can look at a rock, it can fire a laser beam, it can look at the emissions from the laser beam and basically tell us what the rock is made of. We have instruments that look at radiation from space, we have cameras, and the instrument I'm going to talk about is SAM. You can see the label in the bottom left, but it's buried inside the rover, and we either look at atmospheric gases and the composition of the atmosphere, or we dump sample in and heat it up and see what it's made of. It's really a complicated experiment. Florence, actually, when she was at Goddard, spent a lot of time helping us get the electronics, the controller for this instrument going. But it has 3 instruments in it, and it has a fairly complicated gas processing system. And because we don't want to bring any Earth contamination to Mars, there's Florence in a clean suit, basically helping get the instrument assembled. We have a nearly identical instrument, which we operate in the lab on Earth, and we operate that in a Mars environment to model what's going on the surface of Mars in that very cold environment. And so we developed that over a number of years. After the turn of the decade, we were selected in 2004. And after that, we just went to work. And in 2011, the rover was at Jet Propulsion Laboratory. It was turned upside down so we could install SAM in it. And here SAM is on a crane, kind of being lowered into the belly of the rover, getting ready to go to Mars. And then November 2011, it was all assembled on an Atlas rocket, and we launched successfully to Mars. And of course, the big deal is, can you get to the surface safely? Because the atmosphere is very, very, very thin. And so here the entry, descent, and landing, the EDL team, got first word that we were on the surface of Mars, and they're a bunch of happy dudes. They're all doing high fives, and we're on the surface of Mars ready to go in August 2010. And so this was, many of us were out at Jet Propulsion Lab in Pasadena, California at that time. And this is one of the very first images that came down. This was from a camera, a hazard avoidance camera, and the dust cover was on. But you can see Mount Sharp, which is a big mountain in the center of Gale Crater in the background. And so it's just tremendous to see that, just really exciting. And then there was President Barack Obama was on an airplane, actually headed out to the Midwest, I think, for an event. So he called us from Air Force One and congratulated the team. Also congratulated this guy. His name is Babuk Ferdowsi. He's in the upper right. And of course, he got to be kind of famous because he got a mohawk and became known as the Mohawk Guy to celebrate the occasion of the landing of Curiosity rover. And this is the folks from our team that were out at Jet Propulsion Laboratory. There's Florence with the SAM t-shirt on, and everybody's cheering because we're seeing pictures in front of us of the rover on the surface of Mars. And there I am in the center grinning away. Everybody's very happy. We're ready to go to work on trying to understand Mars. This picture was just incredible. There's a imager on the arm of the rover, and it can take pictures of the ground, but since it's the arm, it can move around. And here it took a picture of the camera on the mast. And because it was taking a picture through the dust cover at this point, everything looks a little spacey, but it's just a tremendous picture. It's really one camera looking at the other camera on Mars. So here is our target. This is Gale Crater. It's a 150-kilometer crater, just a huge crater created by when an asteroid or comet came blasting in from space nearly 4 billion years ago. And it was discovered by a guy, Walter Frederick Gale, so they named the crater after him. And over time, the crater eroded and left this central mound. And where we landed, there's kind of a 5-kilometer high mound, a mountain in the center of Gale Crater. We call Mount Sharp. And so we wanted a safe landing space. So that little elliptical area you see in the bottom didn't have a lot of rocks or anything that could destroy the rover on the way in. So that's kind of where we landed. And so this is kind of a little bit of the history of Mars, pointing out where Gale Crater formed almost 4 billion years ago, somewhere between 3.5 and 4 billion years ago. And at that time, Mars, lots of craters were hitting Mars early in the history of the solar system. And Mars was really different. It was probably lots of liquid water around, much warmer than it is today. And of course, the big question is, during that ancient time, when Mars was much more similar to Earth, could life have developed? And here's a history of Earth. And way back, even earlier than 3 billion years ago, 3 GA, we have listed on this timeline, the first evidence of life is present. Cyanobacteria were coming along, and the signatures of them are left in rocks. And it's only very recently in the history of this planet, in the history of Earth, that things like plants and dinosaurs and humans emerged. And so it's really interesting to try and understand if very early in the history of Mars, whether life emerged or not in the form of microbial life, for example. But the major objective of this mission, and our part of it, is looking at Mars with this suite we call SAM, Sample Analysis at Mars, which has 3 instruments and then a fairly complicated solid sample manipulation system. The basic objective of the mission is to try and understand, in ancient Mars, in that very ancient environment which was exposed in the Gale Crater, were the conditions right for life? Was it habitable? And this is just another picture of where we deposit samples into these ovens. We put them in these quartz ovens and we heat them up. And as we heat them up, we look at the gases that come off. You can see on the bottom left the signature of a couple of gases that are coming off. And then when we're looking for organic compounds that are really interesting, then we run them through what's called a gas chromatograph. It basically just separates out molecules in time, and we can try and understand exactly what they are. And so here's an image from space showing where we landed. We named it the Bradbury Landing Site. And if you've got real eagle eyes, you can kind of see there were rockets firing on the way down. And so they blew all sorts of dust in the vicinity of the rover. And so you can see the imprint of that in that little inset there. And then we were supposed to go kind of northeast to the upper left of this landing site. But when we looked off in the distance, we saw this really interesting site. Looked like a little low-lying area, and it was the intersection of different geologies. And so we decided to head over there. And so a day on Mars, since the number of hours in a day is not exactly the same as on Earth, we call it a sol. So the first 50 sols are shown in white in this diagram. And so it took a couple months before we finally got off to this first little site that we wanted to explore. And we were all at Jet Propulsion Lab. Since Mars operates on a different timeline than Earth does, we were all operating on Mars time, because every morning at 10 a.m. on Mars time, we would be sending up commands to the rover from Earth. Listen up, rover, this is what we want to do during the day. And then when the rover did all its science, took its pictures and such, then it would send the data back to one of these orbiting satellites, send it back to Earth, and then we would look at it. And since we were really interested in getting our hands on the data as soon as we possibly could, we operated on Mars time, which shifted by 40 minutes Earth time every day. So we were often sleeping during the day and having meetings at 3 a.m. in the morning and so on. And here are a few of the first really interesting pictures from that site named Yellowknife Bay. And this tells the geologists a lot. Basically, these are layers that were laid down by flowing water. The people who study this for a living immediately say, oh, that's evidence of flowing water. So that was really interesting. We probably thought there would have been water in this ancient environment at some time, and this is kind of proof of it. And the first drill hole we drilled was several months after we landed. It was February 6, 2013. And although the surface looked red, once we drilled into this hole, it turned out looking like mud. And in fact, it was a mudstone, really, really interesting. And so this is just the whole size there is about the size of a quarter, a little bit less, maybe the size of a nickel. And we're basically getting some sample to put into our instruments. And so when we put it into our SAM instrument and heat it up, like I said we did, basically these are some of the gases that come off, oxygen, carbon dioxide, sulfur dioxide, water, and so on. But it's a trace of these gases that kind of tells us, in combination with other instruments, what minerals are there and what the chemical environment was of that ancient lake. And so once we looked at this data and looked at the data from an X-ray diffraction, looked at the data from elemental analysis, we concluded that this ancient environment really was habitable, because it suggested that there had been long-standing water there. In the particular site that we sampled, it probably was formed by an ancient river system. And the mineralogy, the types of minerals that we found, indicated that basically there was a long-term interaction with liquid water. So if there was a lake there, it probably lasted for millions and millions of years. The elements that life needs, that microbial life needs, carbon, hydrogen, nitrogen, oxygen, sulfur, and so on, were all there. And so we concluded very shortly after landing, in the distant past, this probably was a habitable environment. Doesn't mean that there necessarily was life there, but life could have survived there just fine. And so it was a really interesting site. But what we wanted to do is basically save some sample for later on. So we put it in a doggy bag. We stored some samples in those quartz cups and started to move along. And we've been moving along ever since, going up toward the mountain in the center of Gale Crater and exploring different environments, clay units where from space you can see that there's a lot of sulfur compounds and so on. We've drilled a lot of holes. You can see all the nice different colors of the drill holes, which is really interesting. And lots of data, lots more gases released in our heating experiments. And the conclusion, even more firmly established, was that there was a big old lake here, and that as rivers flowed into the lake, you can see that cartoon on the bottom of the bottom right, that basically those deposits, those sediments were laid down in a way that could be interpreted as rivers flowing into a lake. And that's what we derived from taking these images of the landscape. But even after the crater dried out, there was probably underground water coming into the crater and depositing these white veins, which are calcium sulfide veins. One thing about Mars is the atmosphere is very, very thin. And so if we're looking for organics, we have to be careful, because the radiation that comes in from space can break them apart. So it's really a good idea to go deep if one can. And so we learned a lot about that by understanding how the radiation has changed some of these samples. But one thing I want to talk about before we wrap up is methane. And methane is really, really interesting. In the Earth's atmosphere, you know, the atmosphere is mostly nitrogen and oxygen, and there's some carbon dioxide. We're always trying to keep the carbon dioxide down to combat global warming and so on. But there's also a couple of parts per million in the Earth's atmosphere of methane, but most of it comes from biology, from cows, from basically microbes doing things in rice paddies and wetlands and so on. So on Mars, we're very interested. And in fact, we did find methane, and we're really interested these days in trying to understand where it came from. It's in the atmosphere, and most likely it's seeping up from the ground. And it could have been created underground in the past by microbial life. They're called methanogens. Or in fact, there are other ways without biology of producing methane. Olivine and water combining can also produce methane. And so it was really interesting. We've been seeing methane, but intermittent spikes of methane. But part of the objective of our instrument was also look for organics. And the first organics we found were chlorine-containing compounds, chlorobenzene, and then other simple chlorine-containing compounds. The chlorine in these slides is colored green. And so we got that result out. That was really interesting. And then some sulfur-containing compounds, thiophene and other sulfur-containing compounds. And so that's significant. Our colleague Inga Tenkata, in a science article describing some of these organic detections, described the implications of finding these organics in methane, that basically the question of whether life may have originated or existed on Mars is a lot more opportune now that we know that organic molecules were present on its surface at that time. So really interesting results. But of course, we would love to do is find more complex organics, such as are in our DNA, our proteins, and that type of thing. And so we're looking for those. We're going to be looking for those with the next mission, which is going to launch this year. It's a European mission. It's going to launch with support from the Russians. And at Goddard, we developed an advanced mass spectrometer that does gas chromatograph GCMS, but it also ablates a sample with a laser and trying to fish out evidence of some of these complicated molecules. And this mission is going to a really old site on Mars. Here's a geological map of Mars, and the brown areas are very, very old sites. On Earth, all the old sites have been destroyed by plate tectonics and volcanic activity, like we just saw in Toga recently and so on. But we're going to a place called Oxyaplanum, is a selected landing site where there are lots of clays. We're going to dig down and basically see if we can find more complex molecules with another mission. So that'll be launched next year in 2023. We should be getting data from that mission. And so that's kind of a snapshot of what we've been doing on Mars. You can look at more detail of SAM on our website if you like. The URL is up there, or just Google Mars SAM experiment, and there's the URL. And I'll end with this. Florence's father-in-law actually sent us this little limerick here. A few years ago, the Martians sent out a patrol to see what was doing one's soul. They got a big thrill to see over a hill, curiosity taking a stroll. So with that, I'll wind it up.